it goes. And let's see, we're going to go ahead and start sharing, and hopefully everybody sees the little kid. That is my little girl. Let's see, and we want to start with whiteboard. There it is. All right, let's move everybody down here. Whiteboard will be starting up in just a second. Okay, so we are starting an entirely new chapter, and that's chapter 6, and this is electronic structure of atoms is what this is all about. Okay, so this was what chapter 6 is really all about, is electronic structure of atoms, and really what atoms are all about when you really get down to it. And so in the world of chemistry and physics, there's like prior to 1910 and there's after 1910. Prior to 1910, you've got all your alchemists running around with their pointy hats and all that good stuff, trying to turn lead into gold. And after 1910, we actually start to understand what the heck's going on with atoms and molecules and electrons and things like that. Okay? Now, the first thing that we have when we have electronic structure of atoms is we have to realize that the only way we know anything about anything is because we can see it. Literally, if you can't see it, it doesn't exist. Really, if you can't see it, if you can't see it, if you can't touch it, if you can't measure it, if you can't do something, how do you know it's even there? If you think about it, right? And so things do exist. I see Crystal going like, well, what do you mean? There's all sorts of things in this world that I can't see and I can't. Well, yeah, but if I throw enough money at it, if I spend if I put like $1 billion into this great big machine sitting out in Switzerland and France, otherwise known as CERN, yeah, you can see things with the proper equipment that you wouldn't otherwise be able to see. Okay, but prior to 1910, no one knew any of this stuff. And so the first thing that we need to know about is the nature of light. The nature of light. All right, what's light? Well, light are basically photons. They're little particles, but we did not know that prior to around 1910ish or so. Okay, but what we did know is that we have different kinds of light. We have visible light, which is what we can see. We can see that. All right. And for a long time, that was the only kind of light that we even knew about was visible light. And if you see visible light, it goes red, orange, yellow, there it goes. It goes red, orange, yellow, green, blue, indigo, violet in that order. That's the order of the rainbow. Now, if you've ever watched Sesame Street, and this is how I learned this, was watching Sesame Street, there's actually an episode called Elmo Loses His Rainbow. And it's a great episode because I learned about Roy G. Biv, and of course no one ever believes Elmo when Elmo tells him something, and gives Elmo quite the complex. It's not very nice to treat children like they treat Elmo. But the thing that he does is he says, I want to draw the rainbow that I saw so everybody can see the rainbow. And one of the adults says, well, the way this works is that all rainbows go in the same order. They go from red to violet, and you can draw a rainbow as long as you go in that order, and it looks like someone's name, Roy G. Biv. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. It goes in that order. Okay? Now, it turns out that when we talk about light, and for y'all's information, when I went to grad school, I started out as a molecular spectroscopist. That's what I started out as, which meant I used lasers. Okay? I used lasers. That's what it meant. It's a fancy way of saying I had lasers on sharks. And so that's what I used. And so when we talk about light and we were trying to probe things, we would say we are towards the red, and that would be towards the red end of the spectrum. And then we would say towards the blue would be towards that end of the spectrum. Okay, and actually towards the red we would actually say is less energy, and towards the blue we would say is more energy. Because when you're dealing with light, you got to be able to say, which way are you going? It's not enough to say, well, turn the dial on the laser. You would actually say, well, okay, turn it a little bit towards the blue, or turn it a little bit towards the red. Okay, and in fact, if you go out towards beyond what you can actually see, and we go out into the UV, which is beyond violet, because that's what UV means, is ultraviolet. Ultraviolet means beyond violet. We're actually going even more energy, because where are we going? We're going towards the blue. So ultraviolet is even more energy than visible. And then we get out into X-rays beyond that, and then we have gamma rays, which are really energetic, way beyond X-rays. X-rays are the stuff they do in the dentist's office. They check your teeth, they blast you from X-ray radiation, which I really don't like it when they do that. And I always tell them, why do you have to give me an X-ray? And they say, because we want your $200. Now sit still so we can take your X-ray. That's why they want to take X-rays. But every time you take an X-ray, this stuff beyond violet is called ionizing radiation. Ionizing radiation beyond, from ultraviolet on beyond. And ionizing means it produces ions. It also means that if you're ultraviolet or beyond, that it can break chemical bonds. Now, guess what you're made out of? You're made out of chemicals, and specifically DNA. And if you break DNA, guess what can happen to you? You can get cancer, or other bad things can happen. And so every time, not to scare you, but every time you get an X-ray, you run the risk of developing cancer. And there is a very small but non-zero. Non-zero means it ain't zero. There is a chance. It's a small chance. And my colleagues say, Mr. Pierce, you're just being stupid. That's what they tell me. That's what my colleagues say. But you know what? Why get so many X-rays if you don't need them? Right? Non-zero is non-zero. It's just like every now and then. Anybody play the lotto? Anybody play the lotto? I do. Every now and then I put it's $2 nowadays. Every now and then I put $2 down and I say, you know what? This is my trip out of poverty. And I put down my $2, and my colleagues who are more sensible than me, they say, you're just wasting $2. But I look at it this way. It may be 1 out of 300 million or so, right? But that's a non-zero chance. I have a chance. By the way, if I did hit the lotto, I would finish the semester. I would finish the semester. But so there is a chance, and so as you go through X-rays, you definitely are taking a chance. Go ahead and get your dental X-ray. You might as well. And gamma is even more energetic and even more ionizing. Okay. Now, as we go towards the red, you see what I mean by go to the blue, go to the red? It's much easier to say that than say go left or right, because it depends on which way the spectrum's pointing. So if I just say we're going to the red, I'm going to less energy. And if you go to less energy, the first up is infrared. Infrared is in lower energy. Now look, you ever been to Mickey D's? Mickey D's, yeah, it's good, but it's not good for you. And if you notice, they have these lights, these red lights, and you call them heat lamps. And if you stick your hand underneath them, it feels like there's heat coming from them. But it's not so much heat that's coming from those lights, it's actually a form of light that you can't see, infrared radiation. It hits the food, it keeps it warm. Okay. Now, infrared radiation is not ionizing. In other words, it won't break bonds. It'll heat things up, but it won't break bonds. And beyond infrared, we get into microwaves. We get into microwaves if you go red of IR. And that's the same stuff. When we say microwaves, it's the same stuff that's in a microwave oven. In case you don't know, microwave ovens actually, they have a microwave generator in there that produces microwave light. You can't see it, but it's still light. And the microwaves actually interact with the water molecules. Here's a water molecule. And they make the water molecules spin. They actually make the water molecules spin. And it's the spinning of the water molecules that's bumping into the other molecules in the food that actually heats up the food. Okay, and matter of fact, just to make this complete, infrared makes bonds vibrate. They actually go back and forth. Like infrared actually makes bonds do this, and microwaves actually make molecules spin. They spin and they vibrate. And it's actually and that's one way of telling what you have is how does the infrared radiation react with the molecule. It can tell you something about it. And same thing with microwaves, you can actually determine the shape of molecules with microwaves, because how it spins depends on the shape. Just like a top, just like, hey, it's exactly like that. And so if you ever wondered, well, how in the world can us, smarty pants scientists, how can we figure out, what's the shape of a molecule? Well, simply, we put it in a microwave. A sophisticated microwave, but we put it in a microwave, and depending on how it absorbs or emits the microwave radiation, we can tell you about the shape. All right, this is stuff I did in grad school. See, now you really do want to be a chemistry major, right? Yeah, chemistry majors. But anyway, so beyond microwaves, as we head to the red, we have radio waves, and they're the longest, least energetic, or radio waves. Radio waves are the things that your cell phone, for instance, is a radio transmitter and receiver. That's what your cell phone does. It transmits radio waves and it receives radio waves off of these big towers. That's what it does. Okay? And so that is the electromagnetic spectrum. And it's not the scale. For instance, the visible portion is actually quite small compared to the overall range. Now, on the bottom, I had energy, and we had energy going this way. But we also have something called the frequency, and the frequency actually increases as we go to the right, and we have something called the wavelength, and it decreases, and it also decreases as we go to the right. Okay, now that's the general layout of the electromagnetic spectrum. Do you have to memorize this? Well, not really, but it's really handy to know. It's kind of like everything else in this world. You don't have to memorize a lot of things, but it's good to know the general layout of where things are. Okay? So just keep in mind, there is a layout to all of this. All right, now, one thing about light is that it is a wave. At least one possible characteristic of light is that light follows a wave. All right, so it is a wave as it goes through space. That's what light does. And so we've understood waves for a long time, and waves do special things. If you go out in the ocean, you'll see waves, and people observe waves all the time. And as they go around objects, they get spread and they come together, and all sorts of things that waves do. Okay, but all waves have certain characteristics, and one is that the distance from peak to peak, or trough to trough, this is called the wavelength. And we're going to give it a special symbol. All right, that's a lambda. Lambda mu. Yep, lambda. Okay. And sometimes you will see it drawn like this. No, that's a gamma. Sorry, never mind. I'm not up in my. Never mind me on that one. Okay, so there's your wavelength. Okay. Now, how many? Now the time that it takes to go. Now the time as it goes by from wave top to wave top, how many wavelengths you have go by per second. This is called the frequency. How many waves per second? This is waves per second. Okay, and it has its own symbol as well, and it's a funny looking V. It looks like that. There you go. It looks kind of like that. All right, and you may see it drawn slightly different. This is my font. All right, there are many fonts. This is just one. So if you see it looks slightly different in the textbook, it's just because I'm using a different font. Okay. I've had people really go like Mr. Pierce, what's going on? What you're drawing doesn't look just like it. And I'm like going, if you really think about it, they are the same. All right, they really are. Okay. All right. So we have wavelength and frequency. Okay, the wavelength is the distance from one peak to another, and the frequency is how many peaks do you have passing by per second. All right. Now, the relationship between the wavelength and the frequency, and here is your first equation. Remember, it's all about equations. And we say the speed of light is equal to the wavelength times the frequency. Okay, and I'm going to change colors here because I like doing different colors. And this is the speed of light. And the speed of light is 3.00 times 10, what is it, times 10 to the, I always have to look it up. You know, everything is look-upable. And so we say, where is speed of light? There it is, speed of light. There it is, times 10 to the 8th. That's what I wanted to say. Times 10 to the 8th meters per second. Let me fix that C. Meters per second, okay? 3.00 times 10 to the 8th meters per second. Now, that is really hauling along. That is really, really fast. But even as fast as that is, it still takes a little over a second to get to the moon and back. You know, it takes what does it take? I think it's about 8 minutes from the Earth to the Sun and the Sun to the Earth. It's roughly about 8 minutes, I believe. That's how long. So if the moon, pardon me. So if the sun were to suddenly just go out, you know, like a light, all of a sudden collapses in on itself, it would take 8 minutes before you realized what was going on. So it takes that long for it to get to you. So, but light, that's pretty fast when you think about it, you know. It takes 8 minutes to get to the sun. It takes many months with a spacecraft. All right, now, this is a pretty straightforward equation. It's something times something equals something else. All right, and here's the part. Remember what I said? What does it mean when I write something in red? It means do not be that person. Okay? Units are everything. The wavelength must be in meters. And the frequency must be in per seconds. 1/2 or seconds to the -1. That means the same thing, by the way. Or something called a hertz, which is the same thing, Hz. All right. Wavelength must be in meters. Now, remember when we went back on chapter 1 and we said, you know what, there's metric units and then we have SI units, and we said, there's all sorts of metric units, and many times the metric unit that we pick depends on what we're doing at the time. We may measure our height in centimeters, even though the SI unit for length is the meter, but centimeters is a lot more convenient. We may measure the diameter of a red blood cell. We may measure that in micrometers or 1/1,000,000th of a meter because it's more convenient. A lot of these fundamental sort of stuff, like the nature of light, and when we get in the gases, we'll talk about velocity of gas particles. Look, they have to be in SI units. If you use units other than SI units, you will get an answer, and it will be answer C, and it will be wrong. Okay, you will get an answer and you will say to yourself, I've got this. I've got this. Look at that. It's on my calculator. No big deal. All right. And then you get your test back and you say, what the hell happened? Look, it's because you have to be in meters. You must be in seconds. Okay? All right, so let's do some stuff here. Let's just start with this. Okay, so we're going to start with this very simple relationship. To me, this chapter is like, once you get past the definitions, this thing's super easy. So we have C equals, and I'm doing it in red accidentally, but that's okay, I'll switch. And I want to know, and so let me erase this little one right there. So, I wonder why it's doing that. It's updating on me. Alright, so what is the frequency of light with a wavelength of 541 nanometers? Now, remember what I said? I said, you know what? When we use units, many times units that we use are a matter of convenience. All right? If you're talking about visible light, and 541 is green, this is green. And it's not important that you know that 541 is green, but it is. And 540 nanometers is green light. And now, is 541 nanometers in meters? And the answer is no, it's not. It is in nanometers. And we use, and if you're running around in a spectroscopy lab or something like that, no one ever says nanometers. They say, turn the dial to 541. And it's convenient. Everybody knows what you're talking about. They know you mean 541 nanometers, all right? Now, when we do our calculation, though, what we do know for sure, and this is so incredibly important, is what do the units have to be? They have to be in meters. And so let's first off, I want to know what's the frequency, right? What is the frequency? The frequency is this guy right there. And so I'm going to take, and I'm just going to go ahead and just copy this down here, and I'm going to say that the frequency is C over lambda. There it is. Now, if you just simply plug in the speed of light, 3.00 times 10 to the 8th, and then divide it by 541, you will get an answer, but it will be wrong. Okay? So it's very important that we realize, what does it mean to be a nano? Here's how you handle this sort of thing. You know your prefixes. What's a nano? A nano means times 10 to the minus ninth. That's what a nano means, is times 10 to the minus ninth. It's a prefix. And so what that means is times 10 to the minus ninth meters. So you don't have to set these things up so everything converts. All you have to do is remember your prefixes. And you do that, and you say, now we can say with confidence that this is, what is this? This is 541 times 10 to the minus ninth meters, because that's what 10 to the minus ninth means. It means nano. Now, I ask you, is the wavelength now in meters? And the answer is, yeah, it is. It's in meters now. And it has to be in meters. But this is often, and I will put here, often left off. Often left off. You have to put it in meters. Okay, you have to put it, and it's easy peasy. It really is. If you know your prefixes, it's super easy. Okay. Now, is this in scientific notation? The answer is no, it's not in scientific notation, but, and I'm going to put this in, let's see, what color do I want to use? I think I'm going to use green here. It's not, it's not in scientific notation. It is true. It is true, but who cares? Who cares? And the reason is because you can, so if I put 541 times 10 to the minus ninth in my calculator versus, and if I put this in scientific notation, this would actually be 5.41 times 10 to the minus seventh meters if I was to put that in scientific notation. If I put either one of those in the calculator, guess what? The calculator won't care. Calculator won't care. They're the same number. 5.41 times 10 to the minus 7th versus 541 times 10 to the minus 9th is the same number. It's just one you've moved the decimal point over 2 times. That's the difference between the two. And so when I do this on my calculator, I never put it in scientific notation. I just say it's 541 times 10 to the minus 9th. And so we come over here, now that we have this, and we come over here, and we're actually going to just go ahead and plug this in. And so I say, you know what? It's 3.00 times 10 to the 8th meters per second, and it's divided by 541 times 10 to the minus ninth meters. And look, meters cancel. Hey, you know what? And that leaves you with per second. Units cancel. That's why you have to have them in meters. You have to have them in meters. So if you don't have it in meters, units won't cancel. And I take this and I put this in my calculator. It should be around 10 to the 17th. And so what do we got here? 10 to the 15th, somewhere around there. It's a big number. Let's see, 3 second exponent 8 divided by 541 second exponent to the minus ninth. And I get 5.55. 3 sig figs times 10 to the 14th, and that is per second, or we could say hertz, Hz, or we could have said per second. We could have said all three of those things mean the same thing. Okay, I like Hz just because hertz is per second. Okay, and so we have an answer here. All right. And so one of the things to notice about all of this over here is, first off, for visible light, your frequency is going to be around 10 to the 14th. And for visible light, your wavelength is going to be around 10 to the minus 7th, or in the hundreds of nanometers. In the hundreds. So visible runs somewhere around 900-ish. That's a technical term, to around 240 or so. That's visible light, not around 900 to 240. I think it's maybe a little bit further to the red, maybe a little bit further to a blue, but it's around in that range. Okay. Beyond, when you start getting into like 180 nanometers, you start getting into ultraviolet. You start getting around into 1200 nanometers. You're starting to get into the infrared and that sort of thing. Okay. All right. So what's the take home on this? Must be in meters. Your wavelength will very rarely actually be in meters. Very rarely will it be in meters. If you're in meters, it means you're generally in the radio wavelengths in meters. That's what meters is radios. Okay? And very long wavelengths at that. All right? And so let me make sure. Let me try somebody. Let's see. Where do I do this? Let's see. Oh, well, I was going to turn off. Somebody's mic is open. I can hear you clicking your bourbon on the rocks this morning. I hear the ice cubes clinking around. All right. And say, hey, it's never early enough. All right. So, so there you go. So it must be in meters, and it must be in seconds. Usually the seconds part's not a problem. It's the meters part that trips people up. Okay, it's usually the meters part. All right, so moving along here now.
Mr. Pierce, quick
Yes,
question.
yes.
Where do we get the 3.0 times 10 to the eighth? Where did we get that from?
Okay, great question. That's the speed of light. It's a constant. It's the speed of light. By the way, that's the speed of light in a vacuum. In other words, out in interstellar space, the speed of light it's 2.999 something or another, but it's 3.00 times 10 to the 8th meters per second. Speed of light in a vacuum. Now, it's a constant. It's in the back of your textbook. It's on the very back inside of the cover. Matter of fact, it is right. If you can see me, I'm assuming that everyone can see me. It is right there. It's right there. Can you see that? It is right there, right where my finger is on the inside of the back cover. So that's where I got it from. Also, it helps to memorize it, just so that you don't have to look it up. Now, I say that's the speed of light in a vacuum. Now, we're going to assume that the speed of light is always in a vacuum, even though we do things in a laboratory, and we're definitely not in a vacuum in the lab. Speed of light changes depending on what it's going through. So when you go to take physics, and many of you will, I guess, if you become truly a science major, you will have to take, at least a semester or two of physics. I had to do it. It's a rite of passage. We all have to do these things. And you will find that there's something called the refractive index, which, if you wear glasses, that's how they determine, what the thickness and curve of your glasses is, by the refractive index. And things diffract or focused because the wavelength changes depending on the speed, and the speed changes as it goes through the glass material, and so it actually bends depending on the change in the speed of light. Matter of fact, kind of off on a little tangent here, but you can actually slow down the speed of light depending on the refractive index of the material that you're using. You can actually slow down the speed of light to where you can actually walk faster than the light. You can actually have light go into a device. You can go around on the other side and see the light come out a few seconds later. You can actually slow down light. So light actually, the speed depends, but the fastest that you can go is the speed of light in a vacuum. That's the fastest anything goes, is the speed of light. Okay, so where did I get it from? The back of the textbook. That's where I got the number. Does that answer your question? A long way around, but still. All right, so that's the speed of light. All right, as a matter of fact, the same equations can be used for things like the speed of sound. If you plug in, instead of the speed of light, you put in the speed of sound. If you know the frequency, because you know sound has frequency, right? You can calculate the wavelength of sound. It's the same exact equation. I mean, it's a wave. It's not unique to light. You can actually use the same equations for sound calculations. And if you go off and take physics, and many of you will have to use the same calculations. All right, same calculations, except you'll take it further. You'll do what's called thin lens optics is one thing they end up doing. Okay, so this guy comes along, and his name is Max Planck. Max Planck, good old Max, and he's trying to figure out, the wave nature of light. This is around the turn of the century, and the one thing he's trying to figure out is why in the world that if you look at black body radiation, and black body radiation looks like this. You have the wavelength, and it goes red, orange, yellow, green, blue, indigo, violet, red, green, blue, and it goes like that. And of course, you can't see shorter than that towards the red, and you can't see longer than that towards the blue. And if you heat up something, and I don't know if you've ever seen like the eye on a stove. You ever seen the eye on a stove? Y'all have stoves, right? Okay. I pull out these examples and people look at me like I'm crazy. Yes, there are these devices known as stoves, and they have these things on the top called eyes. And if you and if you turn on the stove, it will go from black and it will start to glow, and it will eventually turn red. And if you really, really, really have a stove that can get really super hot, it will actually turn a blue shade of white. It'll white hot. It actually have some blue shades in it. And what's happening here, and this has been well known, is that the distribution of light follows something that looks like this. You can't see it at first, but as you heat up, it kind of spreads out a little bit. So what you see is mostly the red. Okay, and as you really, really get something hot, the distribution starts covering the majority of the visible spectrum as you go out. Okay, and so what you perceive with your eyes, is that this looks kind of red, and this looks kind of blue-white. All right, and so this is what you see. Now, back in the 1800s, this was called black body radiation because they didn't use these eyes on stoves. What they did is, if you take a hollow ball, with a very small pinhole, let me fix up my artwork a little bit here, and it has a pinhole on it, light will bounce around until it can come out randomly, and as it does, it senses light. Remember, light is the only way you know something exists, and the light actually senses what's the temperature. Okay, and the temperature determines what color you have, right? Okay, you get out hot, and so as you heat up this ball, this ball with a small pinhole in it, you can actually get these curves that are in black, red, and blue. You can actually get these curves. And this was a very well understood phenomenon. As you crank up the heat, you move the distribution of the frequencies and the wavelengths, you move the distribution of the wavelengths and the color, you move it out. And you can measure these, okay, depending on the temperature. And if anybody's a photographer, you will know what I'm talking about if you say something called the color temperature. Y'all ever heard that? If you look on your cell phone, you might have even seen on your cell phone, it'll give you options like 40K, 30K, 60K for your cell phone photography. And if you notice, this will actually give it a more blue or cool color. This will be actually more of a warm color or more reddish color. Y'all ever seen that on a cell phone processing? You can actually do things, believe it or not, you can do things with your cell phone, and you can do these things actually with a regular standard camera, and they have something called the color temperature. And it depends on how warm or how cool the picture is, because if you've ever noticed, if you take a picture inside with fluorescent lights, it will tend to look a little bit harsher and bluer than, say, pictures taken outside in the yard. They look different. That's because the color temperature is different. And you can actually adjust these things. And the color temperature comes from this black body radiation and these curves over here. Now, you may say to yourself, well, that's all great. So where does Max Planck figure in all of this? Well, here's the thing. You can calculate these curves. I will not show you how to do it, but it's not hard to do, and it's called the Boltzmann Distribution. And it's a very well-known mathematical function, and you plug in the temperature and you get these distributions. The problem is that it's unbounded. The equations to describe this are unbounded. What does an unbounded equation looks like? It means it goes from minus infinity to plus infinity. That's what unbounded looks like. All right, remember, y'all have calculus yet? You know, you got, yeah, okay. So, not going to throw any calculus out. It just say from mathematical standpoint, what does that mean? It means that if you go out, way out, and we're talking way out, the area underneath the curve is non-zero. You have to go out to infinity for it to reach zero. Of course, you never reach infinity, but mathematically we can handle that. All right, we're smart creatures. We can do it. It's non-zero. Now look, if it's non-zero, it's kind of like hitting the lotto. You know what I said about the lotto? It's 1 out of 300 million, right? But I still buy the ticket. Why? Because there is a non-zero chance that I can move out of Winterville. Okay, and don't get me wrong, I love Winterville. I'm just throwing that out as an example. I live in Winterville. Let me tell you, it's a nice place to live. It really is. It's nice. Nothing ever happens. If you want quiet and boring, Winterville's where you need to be. All right, and so there's a non-zero chance. But look, when you're talking physical things, what do we have way out over here? We go UV, then we go X-rays, then we go gamma rays. We're way out there, right? Remember what I showed you with the spectrum. You get out there, what's out beyond ultraviolet and X-rays? You got gamma rays. Look, I can go out far enough, and I'm out into gamma rays. What that's saying is that even for something cool that's red, you are producing a non-zero quantity of gamma rays, according to the math. According to classical calculations, we should all be dead, because we should all be being zapped by gamma rays at all times. Not just the occasional ones from outer space, but all the time from everything. Because black body radiation technically should be producing a non-zero quantity of very high energy radiation. One photon at an infinite amount of energy is enough to destroy the entire galaxy. Now, obviously, the galaxy's still here, and we're not puddles of goo that have been zapped by. Because this is how scientists think. We're not puddles of goo, so there must be something else going on. Because that's the conclusion. It sounds funny, but it's actually a very serious conclusion. Something's wrong. And so Planck says, and being a good sciencey sort of fellow, if you can't exactly explain it, what you do is you make the math work for you. And so what he said was, you know what? At some point there is a minimum amount of energy. He's going to say, this doesn't happen. Right here doesn't happen. It doesn't happen because there is a minimum amount of energy that you can have. There's a minimum amount of energy. Now, this is actually a big idea, that there's a minimum amount of energy that you can have. Because if you think about it, if you look at how fast something, let's say you're driving your car, is there a minimum speed that you can change your speed? And the answer is not really. You can go from 60 miles an hour to 60.00001 miles an hour to 60.0000002 miles an hour. You can change your speed continuously and smoothly. This goes back to calculus. You have smooth functions, you have discontinuities. And what he did was he says, you know what? There's a discontinuity here. That if you go out far enough, there is a point where you have a discontinuity. Do you see that? You drop to zero, beyond which the area underneath the curve is zero. In other words, he said was, I'm going to introduce something that's going to make this infinite curve bounded. And you know what he called it? He called it a quanta. The minimum amount of energy is now called a quanta. And this is where we get the word quantum from. Like quantum mechanics, quantum energy, quantum stuff that we're fixing to do. So he said basically there's a minimum amount of energy. And so the nice thing about it is if you ever invent something, you get stuff named after you. And we have something called Plonks Constant, which is abbreviated lowercase h, and it is 6. What is it? 6.0? No, it's 6.626. After I see them for the first time, I remember what they are. Times 10 to the minus 4th joule seconds. That's joules times seconds. 6.626 times 10 to the minus 34th, and actually it goes off a whole bunch of decimal places. It's in the book. It's 6.626066957, and believe it or not, there's a lot more decimals behind it. It's a very well measured number. Now, and you may say to yourself, Mr. Pierce, so what? But take a look at this. This is where it's important that you understand how big and how small things are. Check it out. 10 to the minus 34th. Big or small? And really small. Really, really, really small. And so Planck says, and this has been very carefully measured, it's a real thing. Planck says, that represents the smallest quantity of energy that you can have. That's one interpretation. It's not really the smallest possible quantity of energy you can have, but it's one interpretation. And because of the way the math works, this is what you get. You get this Planck's constant, okay? And it's going to appear in some equations that we're about to do. Okay, so summarize after all this stuff that I just went through, but there's justifications. Everything has justifications. If you can't justify something, it's not real, okay? And so we say C is the wavelength times the frequency. And now we're going to say that E, the energy of one photon, is going to be Planck's constant times the frequency. Here's where units matter. What is H? H is joules seconds. Here's H. What is frequency? It is seconds to the -1, right? What's seconds to the 1 times seconds to the -1? When you multiply exponents, you add them together, right? So if you multiply these two together, what do you have left? You have joules. What's joules? Joules is energy. See what I'm saying? Units, units, units. It's all about units. Okay, so this is a good place to take a break. Time flies when you're having fun. This is good, clean fun. So what we'll do is we'll go ahead and stop the recording, and we will, let's see,